Something is moving through space, and nobody knows exactly what it is. That is not how astronomy is supposed to work. The universe is filled with mysteries, but most of them stay politely far away. We discover a strange galaxy. We find an unusual star. We detect a black hole hiding in darkness. Then, slowly, patiently, scientists collect data until the mystery begins to surrender its secrets. But every now and then, something appears that refuses to cooperate, something that moves, something that arrives unexpectedly, something that forces astronomers to ask a question they never expected to ask. What exactly are we looking at? When the Hubble Space Telescope turned its eye toward one particular object racing through the darkness, it found something extraordinary. Not a planet, not a comet, not a normal asteroid, not even a typical visitor from the outer edges of our own solar system. Instead, Hubble captured evidence of an object moving through space at a speed and along a path that suggested something remarkable. It might not belong here at all, and that possibility changes everything, because if an object is not from our solar system, then it comes from somewhere else. Another star, another planetary system, another corner of the galaxy, a place so distant that its home sun may never even be identified. For centuries, humanity assumed the solar system was largely isolated, a collection of planets orbiting our star, a self-contained neighborhood surrounded by unimaginable emptiness. That assumption turned out to be wrong. The truth is stranger. The solar system is not a sealed container. It is more like a city with open roads. Things can enter, things can leave, and sometimes, very rarely, travelers pass through. Imagine standing beside a highway at night. Cars appear from darkness. Their headlights flash past, then they vanish into darkness again. You never learn where they came from. You never learn where they are going. You only know they were there. For a brief moment, that is what Hubble found itself observing. A cosmic traveler. A visitor crossing the vast emptiness between stars, and the implications are staggering, because space between stars is almost impossibly large. The nearest star system beyond our own is approximately 4.2 light years away. That sounds manageable until you remember what a light year actually means. Light travels at nearly 300,000 kilometers every second. In a single second, light could circle Earth more than 7 times. In a year, it covers almost 9.5 trillion kilometers. Multiply that by more than 4. That is the distance to the nearest neighboring star. Human intuition breaks down at scales like these. Numbers stop feeling real. The mind struggles to visualize them. If Earth were the size of a marble, the nearest star would still be thousands of kilometers away. The galaxy is not crowded. It is overwhelmingly empty. A cosmic desert stretching across distances that make entire planetary systems seem microscopic. And yet somehow, against all odds, an object appears, crossing that desert, moving from one stellar neighborhood to another, surviving a journey lasting millions of years. Think about that. Long before humans built cities, long before dinosaurs vanished, long before mammals became dominant on Earth, this object may already have been traveling through the darkness, silently, patiently, drifting between stars, a relic from a place nobody has ever seen, a messenger carrying information from another solar system. And Hubble was watching. But before we understand why astronomers became so excited, we need to understand something important. The universe is constantly trying to fool us. Distance creates illusions. Motion creates illusions. Light creates illusions. Objects that seem close together can actually be separated by billions of kilometers. Objects that appear stationary may be racing through space at incredible velocities. Astronomy is often less about seeing and more about interpreting. When Hubble observes something unusual, scientists do not immediately declare a discovery. They become skeptical, extremely skeptical. Extraordinary claims require extraordinary evidence. That principle has guided science for generations, and nowhere is it more important than in astronomy. The sky is filled with false alarms, instrument errors, optical distortions, random coincidences, data artifacts. Every apparent mystery must survive an assault of scrutiny before it earns credibility. So when astronomers noticed a strange object moving in a way that did not match expectations, they did not celebrate. They investigated. Carefully, methodically, relentlessly, because the consequences of being wrong were enormous, yet the consequences of being right were even bigger. Imagine discovering a message in a bottle floating across an ocean. Now, imagine that ocean is the Milky Way galaxy. The bottle traveled for millions of years. Its origin is unknown, its contents are hidden, but it undeniably came from somewhere else. That is what these objects represent, not messages crafted by intelligent beings. At least not as far as anyone knows, but messages nonetheless. Physical evidence that other planetary systems exist. Physical evidence that material moves between stars. Physical evidence that our solar system is not isolated from the broader galaxy. And this realization forces us to reconsider our place in the cosmos. For most of human history, Earth occupied the center of everything. Then we learned Earth orbited the sun. Then we learned the sun was merely one star among billions. Then we learned our galaxy was merely one galaxy among trillions. Every major astronomical discovery has carried the same lesson. We are not central. We are not special. We are part of something vastly larger. Now another layer is being added. Planetary systems themselves may not be isolated. Material can escape. Material can travel. Material can arrive elsewhere. The boundaries we imagined may not really exist. Stars exchange debris. Galaxies exchange stars. The universe is far more interconnected than it first appears. And somewhere within that realization lies the story of the object Hubble captured. A story involving unimaginable distances, violent gravitational encounters, ancient stellar systems, and one of the most important discoveries in modern astronomy. Because this was not simply a strange object, it was evidence of a process that may be happening everywhere, across the Milky Way, across countless planetary systems, across cosmic history itself. A process that transforms the galaxy into something dynamic and alive. Not a collection of isolated islands, but a vast network connected by wandering travelers. Travelers that drift through the void for millions of years. Travelers that occasionally pass through our neighborhood. Travelers that Hubble can sometimes see. And one particular traveler was about to become famous, because its discovery would force astronomers to confront a possibility that sounded almost impossible. The first known visitor from another star. The day the impossible appeared. For generations, astronomers expected this moment, but almost nobody believed they would actually witness it. The mathematics said it had to happen. The physics demanded it. Planetary systems form in violent chaos. Young stars are surrounded by enormous disks of gas, dust, ice, and rock. Within those disks, planets emerge through countless collisions. Nothing about the process is gentle. Worlds are born through destruction. Asteroids smash together. Planetary embryos collide. Gravitational forces fling debris in every direction. Some material falls into the star. Some becomes planets. And some gets thrown away forever. Astronomers understood this long before they ever found direct evidence. If our solar system had ejected material during its formation, then other star systems must have done the same. The logic was unavoidable. The Milky Way should be filled with wandering fragments. Cosmic castaways drifting between stars. The problem was finding them. Imagine trying to spot a single grain of sand floating through an ocean. Now make that grain of sand black. Make the ocean billions of kilometers wide, and make your observation time only a few weeks. That is roughly the challenge astronomers faced. Interstellar objects should exist. They should be everywhere, but they should also be incredibly difficult to detect. For decades, they remained theoretical. Interesting, probable, but unseen. Then came October 2017, and everything changed. At an observatory perched high atop the Hawaiian volcano Haleakala, a powerful telescope was scanning the night sky. Its mission was simple. Look for moving objects, find asteroids, detect potentially hazardous bodies, catalog anything unusual. Night after night, the system quietly performed its task. Most discoveries were routine. Then something appeared. At first, it did not look revolutionary. It was merely another tiny point of light, one among countless others. But when astronomers calculated its trajectory, alarm bells began ringing. Not because it threatened Earth, because it should not exist. The object was moving too fast. Much too fast. Its path through space was unlike anything they had seen before. Most objects in the solar system follow predictable routes. Even comets traveling from the distant Oort cloud remain gravitationally bound to the sun. They may wander far away. They may take thousands of years to complete an orbit, but eventually they come back. This object would not. Ever. Its orbit was not elliptical. It was hyperbolic. That single fact changed everything. A hyperbolic trajectory means an object is moving fast enough to escape the sun completely. Not someday. Right now. It is not trapped by solar gravity. It is simply passing through, like a car entering a city, crossing downtown, and continuing toward another state. Astronomers checked the calculations, then checked them again, then checked them a third time. The numbers refused to change. The conclusion remained. This thing was not from here. It had arrived from interstellar space, and it was already leaving. The discovery sent shockwaves through astronomy, not because scientists had never imagined such an object, because they had finally found one, after centuries of speculation, after decades of searching. The first confirmed interstellar visitor had appeared. Its official designation was ʻOumuamua. The one signified the first. The I stood for interstellar, and the Hawaiian name carried a beautiful meaning: scout, messenger, a visitor arriving from afar, a fitting title, because this object had traveled farther than almost anything humanity had ever observed directly. The moment astronomers realized what they were seeing, telescopes across Earth swung toward it. Every available instrument joined the effort. Time became critical. Oumuamua was moving quickly, very quickly, at tens of kilometers per second. Every day it became more distant. Every day it grew fainter. Every day valuable information slipped away forever. Observatories raced against the clock. Among them was the most famous telescope ever built, Hubble, orbiting above Earth's atmosphere since 1990, watching the universe with unmatched clarity. For decades, Hubble had revealed black holes, captured distant galaxies, measured cosmic expansion, observed dying stars. Now it joined the hunt, because astronomers needed answers, and Hubble represented one of their best chances to obtain them. The initial observations were already bizarre. The object's brightness changed dramatically, far more dramatically than expected. As it rotated, it became brighter and dimmer in extreme ways. That suggested something extraordinary about its shape. Most asteroids resemble irregular potatoes, lumpy, uneven, misshapen, but still roughly compact. Oumuamua appeared different, much different. Calculations suggested it might be incredibly elongated, perhaps several times longer than it was wide. Imagine a cigar drifting through space, or a gigantic cosmic needle. At the time, some estimates suggested an aspect ratio unlike anything previously observed. Astronomers stared at the numbers in disbelief. Nature rarely produces such extreme shapes. Could the calculations be wrong? Possibly. But every new observation reinforced the mystery. The object continued refusing to behave normally, and then things became even stranger. As researchers tracked its movement, they noticed something unexpected. Gravity alone did not fully explain its trajectory. Something seemed to be nudging it, very slightly, very subtly, but enough to matter. Most comets experience similar effects. As sunlight warms their surfaces, frozen gases vaporize, jets erupt, tiny thrusts alter their paths. A ghost without a home. Finding where Oumuamua came from should have been simple, at least in theory. If you know an object's speed, direction, and current position, you can rewind the clock. Trace its pathward, trace its path through space. Eventually, you should arrive at its point of origin. That works beautifully for many objects. It works for spacecraft, it works for planets, it works for asteroids moving within the solar system. But the galaxy is not a quiet place. It is a gravitational battlefield. Every star is moving, every star is pulling, every star is being pulled. Nothing remains still. The Milky Way itself rotates at astonishing speeds. Our own sun hurtles around the galactic center at roughly 828,000 kilometers per hour. And it is not alone. Hundreds of billions of stars are making the same journey. Imagine trying to identify the exact tree from which a single leaf fell. Now imagine that every tree is running across a continent at hundreds of thousands of kilometers per hour. That is the challenge astronomers faced, because Oumuamua had not been traveling for years or centuries. It may have been traveling for millions, possibly hundreds of millions, maybe even longer. Each passing year added uncertainty. Each close encounter with a star altered its trajectory. Each gravitational interaction blurred the trail. By the time humanity discovered it, the cosmic fingerprints were almost erased. Astronomers immediately began reconstructing the object's journey. Powerful computers simulated the motions of nearby stars. They rewound galactic history. They searched for stellar systems that might have ejected the object. Several candidates appeared, then disappeared. New data changed calculations, potential origins were ruled out, fresh possibilities emerged. The deeper scientists looked, the more frustrating the mystery became. It was like chasing a ghost. Every clue dissolved into uncertainty. No clear birthplace emerged. No smoking gun appeared. No star stepped forward and declared ownership. ʻOumuamua seemed detached from history itself, a traveler without a home, a messenger whose return address had been lost. And that fact revealed something important about the universe. Space is old, very old. The Earth is about 4.5 billion years old. The Sun is roughly the same age. The Milky Way is even older. When humans think about travel, we think in years, maybe decades, occasionally centuries. The cosmos thinks differently. The cosmos measures journeys in millions of years. An object ejected from a distant planetary system can wander the galaxy for longer than entire species exist. Civilizations may rise and fall while it drifts silently through darkness. Mountains may form and erode. Oceans may appear and vanish. The traveler continues onward, unaffected, unhurried, patient. That possibility transformed ʻOumuamua from an astronomical curiosity into something much deeper. Because it may have witnessed epochs of galactic history, not consciously, of course. It is merely a piece of rock and ice, yet its journey spans timescales beyond human comprehension. When our ancestors were primitive mammals hiding beneath dinosaur feet, this object may already have been crossing interstellar space. When the asteroid struck Earth 66 million years ago and triggered a mass extinction, it may already have been traveling. When the first humans learned to use fire, when pyramids rose from desert sands, when empires flourished and collapsed, the traveler continued moving, silently crossing the void. There is something unsettling about that realization. Human history feels enormous to us. It dominates our perspective. Wars, kingdoms, religions, scientific revolutions, entire civilizations. Yet against cosmic timescales, all of it becomes a brief flicker. A spark, a momentary flash against billions of years of darkness. ʻOumuamua reminds us of that. It arrived carrying the weight of deep time, the kind of time that makes human achievements seem fragile and temporary. And yet the mystery deepened further. Because astronomers were not only trying to determine where it came from, they were trying to determine what it actually was. That question proved surprisingly difficult. The first assumption was straightforward. Perhaps it was an asteroid. That seemed reasonable. Asteroids are common. The solar system contains millions of them, rocky bodies orbiting the sun in countless shapes and sizes. But the strange acceleration hinted at something else. Perhaps it was a comet. Comets contain volatile materials, ice, frozen gases, compounds that vaporize when heated by sunlight. Those vapors can create thrust, enough thrust to alter a trajectory. Again, that seemed reasonable. Yet visible evidence remained absent. No dramatic tail, no obvious cloud of gas, no classic comet appearance. The object existed in an uncomfortable middle ground. Too comet-like for an asteroid, too asteroid-like for a comet. Nature had delivered something that fit neither category neatly. And astronomers dislike categories that fail. Science depends on classification. Classification helps reveal patterns. Patterns help reveal understanding. ʻOumuamua resisted understanding. Every attempt to place it inside a familiar box encountered problems. Then another extraordinary possibility emerged. Perhaps the object had undergone a process never observed before. Perhaps millions of years in interstellar space had transformed it. Think about the environment between stars. It is unimaginably hostile. There is no protective atmosphere, no magnetic shield, no comforting warmth, only vacuum. Vacuum, radiation, cosmic rays, extreme cold. Temperatures can plunge toward minus 270 degrees Celsius, just a few degrees above absolute zero. For millions of years, an interstellar traveler experiences that environment continuously. The surface is bombarded by energetic particles. Chemical structures change. Volatile compounds disappear. Materials harden. The object slowly evolves, like a ship weathered by endless storms. By the time it reaches another star system, it may look very different from when it began. Some scientists propose that ʻOumuamua represented exactly this phenomenon, not an unusual object at birth, an ordinary object transformed by an extraordinary journey, a survivor shaped by millions of years in the cosmic wilderness. If true, that idea carried profound implications, because it meant interstellar space itself acts like a giant laboratory. a place where objects are altered over immense spans of time, a place where chemistry unfolds slowly and relentlessly, a place capable of creating entirely new kinds of bodies, bodies rarely seen inside planetary systems, bodies humanity had never encountered before. And that raises another fascinating possibility. If one interstellar object reached us, there must be others, many others, perhaps millions, perhaps billions. The galaxy may be filled with these wanderers, invisible, undetected, passing silently between stars. Most are probably too small to notice, too distant to observe, too faint to detect. Yet statistically, they must exist. Every planetary system produces debris. Every planetary system ejects material. Multiply that process across hundreds of billions of stars. The result is staggering. The Milky Way may contain an immense population of interstellar travelers, a hidden ecosystem of wandering worlds. Most will never encounter another star. Most will drift forever through darkness. Some may collide with planets. Some may be captured by gravity. Some may pass briefly through systems like ours. And occasionally one becomes visible, a fleeting visitor illuminated by sunlight. A traveler emerging from the void long enough for telescopes to notice. That realization changed astronomy, because suddenly the first detection was no longer the end of a search. It was the beginning. Scientists began asking a new question. If we found one, how many more are out there? The answer arrived far sooner than anyone expected, because Oumuamua would not remain alone for long. Within just a few years, another visitor appeared, another object from interstellar space, another traveler crossing the vast gulf between stars. And unlike the first, this one behaved in a way astronomers could actually understand, which made the mystery even bigger, because now there were two visitors, two travelers, two clues. And together they suggested that the galaxy might be far stranger than humanity had imagined. The second visitor. The universe has a habit of changing skepticism into certainty. One strange object can be dismissed as an anomaly. Two begin to look like a pattern. When Oumuamua appeared in 2017, astronomers were thrilled, but they were also cautious. After all, this was the first confirmed interstellar object ever detected. Nobody knew whether it was typical, nobody knew whether it was rare. Nobody knew whether its bizarre behavior represented the norm or an exception. There was only one example. And in science, one example is dangerous. A single observation can mislead. A single observation can create false assumptions. Scientists needed another visitor, preferably many more. The universe did not make them wait long. In August 2019, less than 2 years after Oumuamua shocked the astronomical community, another object appeared. At first, nobody realized how important it was. Just another faint point of light against a sky crowded with stars. But calculations quickly revealed something astonishing. This object was also moving on a hyperbolic orbit. It was also not gravitationally bound to the sun. It was also arriving from interstellar space. The second confirmed interstellar visitor had arrived, officially designated 2I Borisov, named after amateur astronomer Gennady Borisov, who discovered it. And unlike Oumuamua, Borisov immediately began behaving exactly the way astronomers expected. It developed a coma, a glowing cloud of gas. It formed a tail. It released dust. It looked unmistakably like a comet. For scientists, this was incredibly valuable, not because Borisov was less interesting, because it provided a comparison. Suddenly, there were two visitors from beyond the solar system, and they could not have looked more different. Imagine meeting two travelers from the same distant continent. One speaks a familiar language, the other speaks none you recognize. One behaves exactly as expected, the other remains deeply mysterious. That contrast itself becomes a clue. Borisov appeared almost comforting, a normal comet, just from another star system. Its nucleus was estimated to be only a few kilometers across. Its composition looked familiar. Its behavior matched models. For the first time in history, astronomers were directly observing material from another planetary system and discovering something remarkable. It looked a lot like material from ours. That finding carried enormous significance because it suggested the processes that create comets may be commoncy. Stars form similarly. Planets form similarly. Icy bodies form similarly. The laws of physics appear remarkably universal. A comet born around another sun still looked like a comet, still behaved like a comet, still followed the same rules. That might sound obvious, but science advances by confirming assumptions. And until Borisov arrived, nobody knew whether other planetary systems would produce familiar objects or completely alien ones. Now they had evidence. At least some of the building blocks of planetary systems appear strikingly similar across the galaxy. Yet Borisov also revealed differences. Chemical analyses detected unusual characteristics. Certain compositions appeared distinct from solar system comets. Subtle variations hinted at a different birthplace, a different history, a different environment. Imagine tasting water from another continent. It is still water, yet tiny differences reveal where it came from. That is what Borisov represented. A sample of another stellar neighborhood. A glimpse into a planetary system humanity may never visit. A dangerous idea hidden inside the mystery lore. The object itself was fascinating, but the implications were even bigger. Because once astronomers accepted that material can travel between stars, an unsettling question emerged. What exactly is being transported? At first glance, the answer seems obvious. Rock, ice, dust. Nothing more. Simple debris drifting through the darkness. But history has taught scientists something important. Nature often uses simple things to achieve extraordinary results. And nowhere is that lesson more profound than in the story of life itself. You are made of stardust. That statement has become familiar, almost cliché, yet it remains astonishingly true. Every carbon atom in your body was forged inside a star. The oxygen you breathe, the calcium in your bones, the iron in your blood, all were created in ancient stellar furnaces long before Earth existed. When massive stars died, they scattered those elements across space. Eventually, some became part of our solar system. Eventually, some became part of you. In other words, the story of life begins with cosmic recycling. The universe takes material from one place and moves it somewhere else. Without that process, planets could not form. Without planets, life could not emerge. Movement is fundamental to creation, which means interstellar objects immediately raise an intriguing possibility. Could they transport more than minerals? Could they transport chemistry itself? This idea has a name, panspermia, and it remains one of the most controversial concepts in astrobiology. The basic premise is surprisingly simple. Perhaps the ingredients for life can travel through space. Perhaps biological building blocks are not confined to individual planets. Perhaps planetary systems exchange chemical material over vast periods of time. To understand why scientists take this possibility seriously, you must first appreciate how resilient certain molecules can be. Life on Earth exists in astonishingly hostile environments. Microorganisms thrive near volcanic vents, others survive in Antarctic ice, some endure intense radiation, some withstand crushing pressures, some remain dormant for years before returning to activity. Life is remarkably stubborn, far more stubborn than scientists once believed. Experiments have repeatedly demonstrated that certain microorganisms can survive conditions once considered impossible. Vacuum exposure, extreme cold, limited radiation, long periods of dormancy, not forever, but longer than intuition suggests. That discovery forced researchers to reconsider old assumptions. If microscopic life can survive harsh conditions on Earth, what about elsewhere? What happens when an asteroid impact launches material into space? What happens when fragments escape a planet entirely? Could some survive the journey? These questions are no longer science fiction. We know impacts can eject planetary material. We know rocks from Mars have landed on Earth. Thousands of meteorites discovered on our planet originated from the red planet. The evidence is undeniable. Material already moves between worlds, at least within a solar system. The leap from planet-to-planet transport to star-to-star transport is enormous, but not impossible. And interstellar objects make the discussion harder to ignore. Imagine a rocky fragment ejected from a distant world. It enters interstellar space. It drifts for millions of years. Eventually, it encounters another planetary system. Most likely, nothing happens. The object continues onward, but occasionally gravity intervenes. A collision occurs. A capture takes place. Material is delivered. The odds are tiny, yet the galaxy is unimaginably large. Tiny odds multiplied across billions of stars and billions of years can produce surprising outcomes. Scientists remain deeply divided on whether panspermia actually occurs. There is no direct evidence that life has traveled between stars. None. That point is important. The idea remains speculative. Interesting, plausible in certain respects, but unproven. Yet even the possibility changes how we think about the universe, because it transforms the Milky Way from a collection of isolated biological experiments into something more connected, something more interactive, something more alive. Imagine forests separated by enormous distances. Seeds occasionally ride powerful winds from one forest to another. Most never arrive. Most perish. But some succeed. Over time, entire ecosystems become linked, not through constant exchange, through rare exchange. That is the concept. Not frequent transport, not easy transport, just enough transport to matter over cosmic timescales. And cosmic timescales are the key. Humans often underestimate the power of time. 1,000 years feels enormous. 1,000,000 years feels unimaginable. The galaxy routinely operates across billions. Given enough time, rare events stop being rare. They become inevitable. Mountains erode, continents drift, stars orbit, galaxies collide. Processes that seem impossible on human timescales become ordinary on cosmic ones. Interstellar travel by natural objects may be another example. What appears fantastically unlikely during a human lifetime may occur countless times across the history of the Milky Way. That realization carries philosophical weight because it touches humanity's deepest question. Are we alone? For centuries, that question seemed impossible to investigate. The distances between stars appeared too great, the barriers too overwhelming, the silence too complete. Yet every major astronomical discovery has chipped away at that isolation. First, we learned planets are common. Then we learned Earth-like planets exist. Then we learned water appears widespread. Then we learned complex organic molecules exist throughout space. Now we know physical objects move between stars. One by one, the walls separating worlds have become less absolute. The galaxy feels smaller than it once did. Not small in distance, small in connectivity. A subtle but important distinction. And interstellar visitors play a crucial role in that shift, because they are proof that the universe is not static. The cosmos is constantly exchanging matter. Stars are born from older stars, planets form from recycled debris, objects travel between systems. Everything is connected through motion. Everything is connected through gravity. Everything is connected through time. That is the hidden significance of Hubble's observations. The telescope was not merely tracking strange objects. It was documenting evidence of a galactic process, a process operating for billions of years, a process likely occurring throughout the Milky Way, a process humanity only recently became capable of witnessing. And there is another reason this matters, perhaps the most practical reason of all, because every interstellar object represents a scientific treasure. Imagine discovering a sealed container from another civilization. Not an intelligent civilization, a planetary civilization, a natural archive preserving information from a distant world. That is effectively what these objects are. Their chemistry records conditions from their birthplace. Their structure preserves clues about their formation. Their composition reveals details about environments astronomers may never directly observe. Every interstellar visitor is a sample return mission delivered by nature itself. No spacecraft required, no launch costs, no decades-long voyage. The galaxy brings the sample to us. All we have to do is intercept it. That realization has transformed scientific thinking. Researchers are already discussing future missions designed specifically to chase interstellar visitors. The idea sounds almost impossible. An object appears unexpectedly. Scientists rapidly calculate its trajectory. A spacecraft launches, then pursues the visitor through the solar system. The technical challenges are immense. The speeds are extraordinary. The warning times are short, yet the potential rewards are enormous. Because imagine what humanity could learn from a close encounter. Imagine photographing an interstellar object from a few kilometers away. Imagine analyzing its surface directly. Imagine collecting samples. Imagine touching material formed around another star. For most of human history, such a possibility would have sounded like fantasy. Today it is engineering. Difficult engineering, expensive engineering, but engineering nonetheless. And that fact reveals how rapidly humanity's relationship with the cosmos is changing. The first interstellar object was discovered only because modern telescopes happened to notice it. Future visitors may be met by spacecraft. Future visitors may be examined up close. Future visitors may surrender secrets impossible to obtain from Earth. And somewhere among those secrets may lie answers to questions we have not even learned how to ask yet, because the greatest mysteries often emerge not from what we discover, but from what those discoveries force us to imagine. And few discoveries have forced astronomers to imagine more possibilities than the strange object Hubble helped investigate, especially when some scientists began wondering whether the mystery was stranger than anyone dared admit. The hypothesis that ignited a firestorm. Most scientific discoveries follow a familiar path. A mystery appears. Researchers gather evidence. Explanations emerge. Consensus slowly forms. The process is rarely dramatic. Most debates remain confined to journals, conferences, and university offices. But every now and then, a scientific disagreement escapes into the public imagination. And when that happens, the story takes on a life of its own. That is exactly what happened with Oumuamua. Because while many astronomers searched for natural explanations, a small number of researchers asked a question that immediately captured worldwide attention. What if it wasn't natural? The suggestion exploded across headlines. Television programs discussed it, websites debated it, social media amplified it. Suddenly, the first known interstellar visitor was being linked to one of humanity's oldest fascinations: alien intelligence. The idea centered largely around the object's unusual acceleration. As Oumuamua moved away from the sun, observations indicated it was experiencing a slight additional push. Not much, just enough to notice, enough to create a measurable discrepancy. The challenge was explaining where that extra force originated. For most astronomers, the relatively straightforward: some form of outgassing, some form of volatile material, some natural process not immediately visible. After all, nature often produces surprising outcomes. Unknown does not automatically mean artificial. In science, that distinction matters enormously. Yet others argued that the object's behavior deserved broader consideration. Among the most prominent voices was Avi Loeb. Loeb proposed that scientists should not dismiss every possibility prematurely. If the available data did not comfortably fit conventional explanations, alternative hypotheses deserved examination. One such possibility involved something called a light sail. The concept sounds futuristic, because it is. A light sail is an ultra-thin structure propelled by sunlight itself. Photons have no mass, but they do carry momentum. When sunlight strikes a reflective surface, it exerts a tiny force. Normally, that force is negligible, but on an extremely thin sail, the effect can become meaningful. Human engineers have already tested the principle. Space agencies have experimented with solar sails for decades. The physics is real. The technology is real. The question was whether nature could somehow produce an object behaving similarly, or whether something artificial might explain the observations. To be clear, no evidence demonstrated that Oumuamua was an alien spacecraft. None. That point cannot be emphasized enough. The data never established such a conclusion. What emerged was a scientific argument about interpretation, a debate over competing explanations, a debate that became extraordinarily public. And the public loved it, because humanity is naturally drawn toward extraordinary possibilities. We want mysteries to be dramatic. We want discoveries to be revolutionary. We want the universe to surprise us. The notion that a strange object from another star system might be artificial was irresistible. Yet science demands restraint. Evidence must lead conclusions. Conclusions cannot lead evidence. That principle protects science from wishful thinking. It protects science from self-deception. And history provides countless examples of why that protection matters. For centuries, people interpreted mysterious lights as supernatural phenomena. They interpreted unusual events as divine messages. They interpreted unknown objects as evidence of extraordinary forces. Again and again, natural explanations eventually emerged. Lightning, meteorites, auroras, comets, disease, earthquakes. Nature consistently proved more complex than human imagination initially assumed. Astronomers therefore approached the alien hypothesis with intense skepticism, not because it was impossible, because extraordinary claims require extraordinary proof. And the proof simply was not there. The available observations were limited. The encounter was brief. The object was already gone. Scientists were attempting to reconstruct an entire reality from fragments of information, like detectives investigating a crime scene after most of the evidence has vanished. As additional studies appeared, many researchers proposed new natural explanations. Perhaps hydrogen was escaping from the object, perhaps nitrogen ice played a role, perhaps unusual physical properties accounted for the acceleration. Each idea had strengths. Each idea had weaknesses. The debate continued. Years later, it still continues. That ongoing uncertainty frustrates some people. They want a definitive answer, a final verdict, a clean resolution. The universe rarely provides such comforts. Sometimes mysteries remain mysteries. Sometimes the available evidence simply runs out. And that may ultimately be the fate of Oumuamua, because the object is gone, far beyond the reach of any existing spacecraft. Far beyond detailed observation. Every year it becomes more distant. Every year it fades deeper into darkness. The opportunity has passed. All humanity possesses now are the measurements collected during its brief visit. A handful of clues, a short encounter, a puzzle whose most important witness has already disappeared. There is something almost poetic about that. The first known interstellar visitor arrived unexpectedly, generated worldwide fascination, raised profound questions, then vanished forever, like a stranger appearing from fog, speaking a few cryptic words and walking back into darkness. No explanation, no farewell, no closure, just questions. And perhaps that is why the story resonates so deeply, because it mirrors humanity's relationship with the universe itself. We inhabit a cosmos filled with mysteries: dark matter, dark energy, black holes, the origins of life, the fate of the universe. Questions vastly larger than ourselves, questions that often reveal just how little we truly know. The discovery of Oumuamua was not important because it provided answers. It was important because it exposed ignorance. It illuminated gaps in understanding. It revealed assumptions that may need revision. That is how science advances, not by proving we are right, by showing us where we are wrong. And astronomy has a long history of humbling humanity. Earth was not the center of the universe. The sun was not unique. The Milky Way was not the entire cosmos. Each revelation forced us to abandon comforting beliefs. Each revelation expanded our perspective. Interstellar objects may represent another step in that process. They remind us that planetary systems are not isolated. They remind us that the galaxy is dynamic. They remind us that the universe is still capable of surprising us. Perhaps most importantly, they remind us that ignorance is not failure. Ignorance is opportunity. Every unanswered question points toward future discovery. Every mystery identifies territory still unexplored. Every uncertainty marks the edge of human knowledge, and Oumuamua sits directly on that edge. A strange traveler from another star, not fully understood, not fully explained, perhaps never fully explained, yet valuable precisely because of those uncertainties. Because mysteries force curiosity. Curiosity drives exploration, and exploration has carried humanity from caves to continents, from oceans to orbit, and from orbit toward the stars themselves. The object Hubble helps study may never reveal all of its secrets, but it has already accomplished something remarkable. It has expanded the boundaries of the known universe, not physically, intellectually. It has shown us that visitors from other star systems are real, not theoretical, not hypothetical, real. And now that we know they exist, a new challenge emerges. The challenge is no longer finding the first one. The challenge is preparing for the next, because the next generation of telescopes is about to transform this field completely. And when that happens, interstellar visitors may stop being rare curiosities and become a regular part of astronomy. The age of cosmic surveillance. For most of human history, the night sky changed slowly. Stars rose, stars set, constellations drifted across the seasons. To ancient observers, the heavens appeared eternal, predictable, unchanging. That illusion survived for thousands of years. Then technology shattered it. The modern universe is not still. It is alive with motion. Asteroids race through the solar system, comets plunge toward the sun, stars explode, black holes collide, galaxies merge. And now we know interstellar visitors occasionally cross our cosmic neighborhood. The challenge is not whether these events happen. The challenge is seeing them. For centuries, humanity lacked the tools. The sky was simply too large, too dark, too vast to monitor effectively. Imagine standing on a beach and trying to notice a single grain of sand tossed into the ocean. That was astronomy's problem. The universe generated countless events, most passed unnoticed, most vanished before anyone knew they occurred. Oumuamua demonstrated this perfectly. Astronomers did not detect it as it approached the solar system, They found it after it had already rounded the sun, after it had already begun leaving. In many ways, humanity almost missed the first confirmed interstellar visitor entirely. That realization was sobering. If one object could slip through nearly undetected, how many others had already passed by? How many cosmic travelers had entered the solar system before humans possessed adequate instruments? How many had arrived and departed while nobody was watching? The answer is almost certainly a lot, possibly thousands, possibly millions, throughout Earth's history. The universe was not suddenly producing interstellar visitors. Humanity was simply becoming capable of noticing them, and that capability is about to increase dramatically. Astronomy is entering what might be called the age of cosmic surveillance. Not surveillance in the sinister sense, surveillance in the observational sense. The ability to monitor enormous portions of the sky continuously, to detect changes quickly, to identify moving objects automatically, to spot the unexpected before it disappears. The most powerful example of this transformation is the extraordinary new generation of sky survey telescopes. These instruments are fundamentally different from traditional observatories. Historically, telescopes operated like microscopes. They focused on specific targets: a galaxy, a planet, a nebula. Astronomers chose an object and studied it carefully. Modern survey telescopes function more like security cameras. They repeatedly scan enormous regions of the sky, night after night, searching for anything that changes, anything that moves, anything unusual. The strategy is revolutionary, because many astronomical events are temporary. A supernova brightens, then fades. A comet appears, then vanishes. An interstellar object passes through, then disappears forever. Miss the event, and the opportunity is gone. Continuous monitoring solves that problem, or at least reduces it. One of the most important facilities leading this revolution is the observatory now known as the Vera C. Rubin Observatory. Perched high in the Chilean Andes, this remarkable instrument represents one of the most ambitious astronomical projects ever undertaken. Its mission is breathtakingly simple: photograph the entire visible southern sky repeatedly, again and again, year after year, generating an unprecedented record of change throughout the universe. The numbers involved are staggering. The observatory produces enormous volumes of data, far beyond what human astronomers could analyze manually. Computers perform much of the initial work. Algorithms identify anomalies. Software flags moving objects. Artificial intelligence assists classification. Modern astronomy increasingly resembles information science. The telescope gathers data. Machines help find the patterns. Humans interpret the meaning. For interstellar objects, this transformation could be historic. Some estimates suggest future surveys may discover many such visitors every year. Not one every few years, not one every decade, many, perhaps dozens, perhaps more. Suddenly, the field could shift from scarcity to abundance, and abundance changes everything. Imagine being the first person in history to discover fossils. Every specimen seems miraculous. Every fragment feels unique. Now imagine discovering an entire valley filled with them. Patterns emerge, categories emerge, understanding accelerates. That is what astronomers hope will happen with interstellar objects. The first discovery proved they exist. Future discoveries may reveal how common they are, how diverse they are, how planetary systems actually evolve across the galaxy. Each new visitor becomes another data point, another clue, another chapter in a much larger story, and Hubble remains an important part of that future. Although newer observatories are joining the search, Hubble still possesses unique capabilities. Its location above Earth's atmosphere allows extraordinarily sharp observations. Once a new interstellar object is identified, Hubble can often help characterize it, measure it, track it, study it in detail. The telescope that helped investigate ʻOumuamua and Borisov continues contributing to one of astronomy's newest frontiers. There is something remarkable about that. When Hubble launched in 1990, nobody knew interstellar objects would become one of its scientific targets. At the time, the first confirmed interstellar visitor remained nearly 3 decades away. Yet Hubble endured, decade after decade, repair mission after repair mission, continuing to observe a universe that consistently revealed surprises. That longevity reflects a broader truth about exploration. The greatest discoveries are often the ones nobody picks. Astronomers did not build Hubble specifically to study interstellar visitors. Yet when those visitors appeared, Hubble was ready. Prepared instruments frequently encounter unexpected wonders. That pattern repeats throughout scientific history. The microscope revealed microorganisms, radio telescopes revealed pulsars, space telescopes revealed exoplanet atmospheres. New tools create new realities, and new realities create new questions. Interstellar objects are generating many such questions. How many exist within the galaxy? What fraction originate from planetary systems like ours? What fraction come from entirely different environments? How far do they travel? How long do they survive? What stories are hidden within their chemistry? These questions may seem abstract, but they connect directly to one of astronomy's grandest goals: understanding how planetary systems form. Because every star system is an experiment conducted by nature, a different arrangement of planets, a different history of collisions, a different gravitational architecture, a different outcome. Most of those systems remain impossibly distant. Even our most powerful telescopes struggle to resolve fine details. Interstellar objects offer another approach. Instead of traveling to those systems, fragments of those systems come to us. The visitors carry evidence. Evidence that can be analyzed directly. Evidence that may reveal processes invisible from afar. In a sense, every interstellar object is a witness to events that occurred around another star, a witness to planetary formation, a witness to gravitational violence, a witness to cosmic history. The challenge is learning how to question the witness properly, and eventually humanity may do more than observe. Eventually humanity may intercept. Several mission concepts already exist. Some involve rapid response spacecraft. Others involve advanced propulsion systems. Some remain purely theoretical, yet all share the same vision. Do not simply watch the next visitor, go meet it. The idea sounds ambitious, because it is, but so did landing on the moon, so did exploring Mars, so did placing a telescope in orbit around Earth. Human history is filled with achievements that initially seemed impossible, and interstellar visitors represent an irresistible target, a piece of another solar system passing through our neighborhood. The scientific temptation is enormous. Sooner or later, humanity will try. The question is not whether, the question is when. Because once we begin visiting these travelers directly, the mystery enters an entirely new phase, and what we learn may transform our understanding not only of the solar system, but of the Milky Way itself, chasing a visitor across the void. Seeing an interstellar object is one thing. Reaching it is another matter entirely. The difference between those two achievements is the difference between watching an airplane cross the sky and catching it with your bare hands. Interstellar visitors do not arrive politely. They do not slow down. They do not wait. They tear through the solar system at extraordinary speeds. By the time astronomers recognize what they are looking at, the object is often already racing away. That reality creates one of the greatest engineering challenges in modern space exploration. If humanity wants to study one up close, we must catch it. And catching it may require some of the fastest spacecraft ever built. To appreciate the difficulty, imagine standing beside a highway and noticing a vehicle moving faster than anything you have ever seen. Now imagine you must build a car capable of catching it. Only after spotting it, only after determining its route, only after calculating where it will be months or years later. That is essentially the challenge engineers face. The first confirmed visitor, ʻOumuamua, was already departing when scientists understood its significance. Launching a mission became impossible. Even the fastest spacecraft humanity has ever built could not realistically intercept it. The opportunity vanished almost immediately. And that loss hurt, because opportunities like that are incredibly rare, or at least they seemed rare at the time. Astronomers had spent generations waiting for proof that interstellar visitors existed. Then one finally appeared, and before anyone could react, it was gone. The experience produced a valuable lesson. Humanity needed a plan. Waiting until the next discovery would not be enough. Future missions would require preparation long before the next object arrived. That realization triggered serious discussions within the scientific community. How do you build a mission for a target that has not been discovered yet? How do you design a spacecraft without knowing where it will go? How do you prepare for an event that could occur next year or 20 years from now? The answer lies in flexibility. Instead of building a mission around a specific object, engineers began imagining spacecraft designed to respond rapidly to whatever appears. A cosmic emergency response team, always waiting, always ready. The concept sounds simple. The reality is extraordinarily difficult. Spacecraft require years to design, years to construct, years to test. Interstellar visitors offer only short notice, sometimes months, sometimes less. The mismatch is obvious. Preparation must happen in advance, long before the target exists, or at least before the target is known. Several mission concepts have emerged from this challenge. Some propose spacecraft parked in strategic locations throughout the solar system, waiting, dormant, prepared for activation. Others envision highly adaptable designs capable of launching quickly once a target is identified. Still others explore advanced propulsion systems capable of achieving unprecedented velocities. Each concept reflects the same fundamental truth. Speed matters, because interstellar objects move incredibly fast. Consider what happens when an object falls toward the sun from interstellar space. Solar gravity accelerates it. The object gains velocity. By the time it reaches the inner solar system, it is often traveling tens of kilometers per second. That speed is difficult to comprehend. At 30 kilometers per second, an object covers more than 100,000 kilometers every hour. In a single day, it can travel farther than the distance between Earth and the Moon several times over. The visitor is not strolling through our neighborhood, it is sprinting, and humanity must sprint even faster if we hope to catch it. One proposed solution involves using gravity itself. The same force that launches these travelers can help pursue them. Space agencies have long used gravitational assist. A spacecraft flies near a planet. The planet's motion transfers energy. The spacecraft leaves with increased speed. It is one of the most elegant tricks in astronautics, a kind of cosmic slingshot. Many of humanity's greatest robotic explorers relied on it. The twin Voyager spacecraft, the Galileo mission, Cassini, New Horizons. Without gravitational assists, many historic journeys would have been impossible. Future interstellar interception missions may depend on the same principle. Another possibility involves solar sails, large reflective surfaces pushed by sunlight. Unlike conventional rockets, which eventually run out of fuel, solar sails continue receiving momentum from photons. The acceleration is small, but over long periods, it accumulates. Given enough time, remarkable speeds become possible. What once sounded like science fiction increasingly resembles practical engineering. The boundary between imagination and reality keeps moving. That has always been the pattern in space exploration. Yesterday's fantasy becomes today's experiment. Today's experiment becomes tomorrow's routine operation. Humanity's first satellites seemed miraculous. Today, thousands orbit Earth. Landing on the moon once appeared impossible. Now, multiple nations plan lunar missions. Interstellar interception may follow the same path. Difficult, expensive, yet ultimately achievable. And the scientific rewards would be extraordinary. Imagine approaching an interstellar object from only a few kilometers away. The blurry point of light becomes a world, not a large world, perhaps only a few hundred meters across, perhaps a few kilometers. Yet a world nonetheless, a landscape never seen before, material formed around another star, geology shaped by another planetary system, a relic from a place humanity may never physically visit. The first close-up images alone would transform astronomy. Consider what happened when spacecraft first visited asteroids and comets. Before exploration, many scientists imagined relatively simple objects. The reality proved astonishing. Bizarre shapes, towering cliffs, unexpected chemistry, complex histories. Every close encounter revealed surprises. Interstellar objects would likely do the same. Perhaps even more dramatically, because these are not merely distant cousins of solar system bodies. They are immigrants from entirely different stellar environments. Their histories may be radically different. Their compositions may challenge expectations. Their structures may reveal processes never before observed. Every detail becomes valuable. Every measurement becomes important. Every image becomes a clue. And there is another reason scientists are eager, perhaps the most profound reason of all. A close encounter would provide certainty. Much of the debate surrounding Oumuamua exists because observations were limited. The object remained far away, small, difficult to resolve. Scientists were forced to infer characteristics indirectly, shape estimates, composition estimates, behavior estimates. Close-range observations eliminate many uncertainties. Instead of guessing, you see. Instead of inferring, you measure. Instead of debating possibilities, you examine reality directly. The difference is transformative. It turns mystery into investigation, and investigation into understanding. That transition represents the next stage in humanity's relationship with interstellar visitors. The first stage was discovery, finding them. The second stage is characterization, studying them from afar. The third stage will be exploration, meeting them directly. And beyond that lies an even more ambitious possibility, not merely visiting these travelers, returning samples from them, bringing pieces of another solar system back to Earth. The idea sounds almost unbelievable, yet so did many achievements that humanity has already accomplished. And if that day comes, if scientists one day hold material from another star system inside a laboratory on Earth, it may mark one of the most important moments in the history of astronomy. Because then the mystery will no longer be observed through telescopes. It will sit directly beneath a microscope. And what it reveals could change how we understand our place in the galaxy.